My project here today is to put a replacement ignition on a Briggs & Stratton twin cylinder 18 horse vertical shaft engine. The model is 822707, but I'm going to do something that I've never done before. I'm planning on using the old failed Magneto as a source for the trigger signal for the automotive type battery powered ignition. So this is the first time I've ever done that. I'm Ed Stoller. I'm a retired engineer, turned 82 last week, and for the last 25 years my main hobby has been to play with replacement ignition systems for small engines. So my test setup here is I have a 10 horsepower cast iron Briggs engine. It's got no piston, no valves, no camshaft, and but it's driven by a treadmill motor here. The treadmill motor powered by a variac, where I can dial in the power going to the treadmill motor to set the speed for the engine simulator. Constant speed's important because I use a laser tack to measure my RPMs, and I use a timing light to check my spark timing. The reference point for the Briggs setup is right beside the armature on the for the Magneto that's set up on there. I also have an oscilloscope. It's called a USB oscilloscope. Has a probe. I connect the probe to the voltages that I want to look at, and the scope digitizes the voltage about 1,000,000 times a second, sends a data stream over to a laptop computer. The laptop can put together a waveform for what the voltage looks like over time, and also measure the peak positive voltage and the peak negative voltage and a whole bunch of other things for me. So this is what I use to do most of the work to develop an ignition system. What we have here is a Magneto from an old point condenser ignition system. So this is pretty old, but the windings for the primary are very uncluttered by all the other stuff around. So it makes a good for illustrating that. But now, magnet wire is a solid copper wire, and it has a varnished coating on it for an insulator, and that's what the primary winding is made of. It carries a lot of current, so it's a pretty heavy gauge wire. I've never known them to fail, never even heard of one failing. So this is very reliable winding. The secondary winding for the high voltage for the spark plug is lots and lots of turns of very, very fine wire, and that's the winding that fails on them. So the whole interest in this whole project is in these two wires here in the primary winding. Now this one end of the primary is connected off to a ground wire. The ground wire here, there's another wire in there, and that wire would go off to the high voltage winding, the secondary winding. So if I were going to use this for replacement ignition, I would just cut that off to get it out of the way. But okay, we have still an open issue with what is the polarity of this primary winding that we're using for an output. And one of the mistakes I made in this project was not keeping track of which end of the primary winding was grounded. So I went back to my stash of ignition coils, and I put each one on the simulator to tell me whether the tall positive pulse is facing up under what polarity. And I was a little surprised to find that all of the Briggs & Stratton ignitions were the same, that all of them had one end grounded. It turns out that the end that was grounded is the end we need grounded, so problem goes away. The other end went to the kill switch wire connection. So it looks like all we need to do is to use the kill switch wire output from the primary winding for our trigger coil. Also noticed 3 of these coils did not have a ground screw, and instead it had a ground connection for the primary welded to the frame. So if that's the case, what we could do is use the mounting screw to hold the solder lug bracket and just run a diode from where the kill switch wire was connected to one of the lugs on our terminal strip, connect our green wire to it. The band of the diode has got to be facing the green wire. So it's about as simple as any modification I could ever come up with. One of the trigger coils I've been using on the engine simulator, and the configuration of this is worth noting. This is a final configuration that I came up with in the course of my project. I put this together after I was doing the parts list and thing. So this is indeed the final configuration. You'll see other configurations, so you don't get confused. Electrically they're probably the same, but physically things kept getting simpler. For this one, we have the lug here. It's a 3/16 spade lug for the kill switch wire. I just mounted a companion connector to that for a quick connect, which is crimped and soldered to the diode. So for the installation, all we have to do is plug these things in. The other end of the diode goes to the green wire that'll go off to the ignition coil. If we did flip the coil over, that would reverse the polarity for the primary winding, and at least for the GM LS2 Ignition Coil, it would not work because the short pulses would be on the top and the voltages would be too low. Before I forget it, you'll notice there's a cylinder side for the old trigger in the old Magneto, and all of that's now dysfunctional, so I chose to have the connections out where I could see them and get to them. So it's not a mistake or an error. It's just this being not a Magneto anymore, we don't need to pay any attention to that. What I'm going to do here is connect my probe to the actual output so that we can start out by seeing a picture of what we're actually starting with for a trigger voltage. Okay, I've connected the probe to the primary winding ends from the Magneto. So this is a signal of what we're starting with. You can see the positive peak is like 4 volts and the negative voltage peaks are about 1.5 volts. The RPM here is about 300 RPM, and this should be just below the speed where the trigger coil would break threshold and start the ignition putting out sparks. Okay, I have the probe now connected to the green output wire, which is also connected to a live ignition coil. My ignition coil is grounded, and the positive power for it is connected to a battery. We don't have a spark yet because we're cranking at about 215 RPMs, and we can see that the output voltage is only about 2.5 volts. So as we bring up, it's very important that we do not have a spark too early. Okay, at this point we do have a spark. Actually, it shows up on the scope as radio frequency interference, and it's right on top of the trigger pulse. So from here to here is the trigger pulse. The spike that's going above that is radio frequency interference from the firing of the spark plug. So it looks like the spark timing is right on top of the trigger pulse. We ran the failed Magneto with the slight modifications on the engine simulator, put out sparks just fine. So I think it's time to move it over to a real engine with actually fuel and air. So we have the system is set up here. I noticed when I was running this on the simulator that the first spark started at about 260 RPM, and I usually like it like 300 to 450 RPM. So when I mounted the trigger coil here that looks a little bit like a Magneto on the flywheel, I used a shim, 18,000 shim to set my air gap. That should raise the RPM for the first spark up to around 300. Okay, the next thing we need to do is mount the ignition coils on the engine and hook it all up. We're using 2 GM LS2 ignition coils. Each coil services 1 cylinder. The coil has 4 wires on it normally. There's a red wire that provides the DC voltage because this is a battery powered ignition. It's not powered by the Magneto, which isn't anymore. And we have that green wire coming in as the trigger signal, which tells the ignition when to fire. And below we have 2 ground wires. One is brown for a computer ground, and the other one's black for frame ground. I tie those 2 grounds together at the connector and just bring out the black wire and connect it to ground. The installation we're doing here is on a tractor that we're going to junk when we're done. So I've made this installation temporary, and so I ran ground wires between all the parts because the sheet metal here is pretty rusty. For the connections, it's pretty simple. We have this wire here that used to be the kill wire. I got it repurposed into the trigger for the coil output wire, and I just bring it out here and tie it to the trigger inputs to the 2 coils. So, you know, the trigger is going to handle both coils, no problem. The red wire, the power lead, is those 2 are connected together, and that goes off to a lead that I'm going to connect directly to the battery. When you install this on another machine, you're going to have to make provisions for a fuse and a switch. The switch for the Magnetos does not work for battery powered ignitions, so it's the wrong type of switch. So you're going to have to make other provisions for switching the power on and off. You could put a toggle switch on the dashboard, or you could replace the original key switch with one that's designed for a battery powered ignition. I'll turn the gas on here, and I think we're ready to crank it. We'll see what happens. It would help if I hooked the ignition up. knock the wire off for the ignition. When I was watching a video of this first run we had, I noticed that some white vapors were coming out of the carburetor here as I just started to crank the engine, and I am sensitive to a problem we have, particularly with overhead valve engines, of the advanced spark firing a little bit too soon in the RPM. So what I'm going to do here is I'm going to reset the air gap on our trigger coil to about 23 thousandths and rerun the engine to get another data point on how it runs. And then I'll follow that up with moving the ignition back to the engine simulator, and I can measure what that RPM is. Okay, what I did here is I loosened the screws that hold the trigger coil to the flywheel, and I put a business card in there. This happens to be a Rock Auto card that I measured with a micrometer to be 23 thousandths of an inch. So with this shim in there, I reset these screws, and that should give me a new air gap of 23 thousandths. And when I move the ignition system back to the engine simulator, I can do the same procedure, get the same air gap, and then get a number for what the RPM is for the first spark. So it seems like the engine starts fine and runs fine. So I think this is the last time I need to run this new ignition. We started with a question as to whether or not we could use a failed Briggs & Stratton Magneto for a trigger coil, and from the way this is performing, I think this makes an excellent choice for a trigger coil. It gives me a nice range for adjusting the air gap, and performance seems to be just fine. Spark timing would be the same as the original engine, almost. I think we got us a good ignition here. I moved the ignition system back to the simulator and installed it, and used that card from Rock Auto for the set the air gap to between probably 20 and 23 thousandths. I brought the RPM down to where I just begin to get a spark. It's like 347 RPM. So that's good. So I think a good air gap would be around 23 thousandths. While we're here, I decided I'd take a look at the trigger signal on the oscilloscope, and we can see that right at 1, 2, 3, it's about 3.5 volts, which is seems to be normal. On top of the trigger bolt, I can see a radio frequency interference from the spark plug. So it's piled just right on top of the trigger pulse. So that's showing me that the spark, at least at this RPM, which is 347, is just right on top of the timing pulse. With the parts assembled, the assembly here looks pretty simple. I'm going to be looking for somebody that maybe would want to provide a parts kit, because there's a lot of little parts that cost a little bit of change in this thing, and some people would probably like it assembled, and I would think the kit should include a plastic feeler gauge for installing it. So if somebody wants to be a supplier of these kits, they can contact me.